There are places on this planet where time feels suspended, where silence dominates the landscape, and the wind is the only sound that dares to speak. In the vast, frozen reaches of the southernmost continent, where the air bites at the skin and the sun arcs low over the horizon, a wall of ice stretches for hundreds of miles, glittering like a fortress built by the hands of ancient gods. It has stood through ages of storms and stillness, a monolith carved by time itself, towering above the restless seas below. For centuries, it seemed immovable, eternal. And yet, something has changed. In the cold heart of this desolate region, a fracture has emerged. It didn't announce itself with thunder or fury, but with the soft, ominous groan of ice under pressure, barely audible, yet deeply unsettling. At first, it was subtle, almost unnoticeable. Just a thin line running across the surface, a slight shimmer in satellite imagery, dismissed by many as another seasonal crack in an ever-shifting landscape. But the line grew. It widened. It lengthened. And soon, it became undeniable. A massive, towering wall of ancient ice is beginning to break apart, and it is doing so at a scale that demands the world's attention. The immensity of this structure is difficult to grasp without standing before it, without feeling the sheer weight of it in the air. It is not just a sheet of ice, but a massive, towering cliff face that extends for hundreds of kilometers, rising high above the ocean like the edge of a frozen continent. The color of it shifts with the light, from blinding white under the midday sun to deep, shadowy blue as twilight begins to fall. Its surface, jagged and rough in some places, is smooth and glass-like in others, as if frozen mid-motion. Every crack, every ripple, every shadow etched into the ice tells a story, of storms weathered, of seasons past, of pressure slowly building beneath the surface. Travelers and researchers who have ventured near the wall speak of an eerie, almost supernatural atmosphere. They describe the ice as alive, not in the literal sense, but in the way it reacts, in the way it groans and shifts, echoing through the air like the deep breathing of something ancient and powerful. Standing in its presence, one cannot help but feel small, insignificant. It is a place where time feels heavy, where history is layered in every frozen inch, where the weight of the earth itself seems to gather in stillness. And now, the stillness has been broken. Images from above show a landscape in transition, no longer static, but unraveling. Enormous slabs of ice, once seamlessly connected, are now drifting apart with glacial slowness and terrifying inevitability. The cracks snake across the surface in chaotic patterns, revealing darker ice beneath, ice that has not seen daylight for tens of thousands of years. And as each day passes, the separation grows. Not dramatically, not explosively, but with a quiet persistence that is perhaps even more unsettling. The scale of this fracture is almost unfathomable. We are not witnessing the collapse of a single block of ice, nor the routine calving of an iceberg. This is something much larger, much more profound. This is the unraveling of a system. A structure so vast, its collapse could trigger consequences far beyond the bounds of this frozen wilderness. But for now we wait. Watching. Listening. Trying to understand what we are seeing. And what it might mean. For now, no official statements can fully capture the magnitude of what is happening. Scientists have urged caution, waiting for more data, more confirmation, more time. But the ice isn't waiting. It continues its slow, deliberate transformation, creaking and shifting under its own weight, responding to forces deep within its core. The world, for the most part, remains unaware. But those who are watching closely, those who study this remote, mysterious place, they know that something significant is unfolding. And as the pieces begin to fall away, as the vast white frontier fractures and changes before our eyes, one question begins to rise, slowly, ominously, like mist off the polar sea. What comes next? Something that vast, something that ancient, does not simply fracture without reason. Nature is deliberate, even in her most violent moments. For every landslide, for every erupting volcano, for every collapsing glacier, there is a story that leads up to it, often whispered quietly in the background long before the world begins to pay attention. And as we begin to trace the footsteps of this ice giant's unraveling, one possible cause begins to surface, not with certainty, not with consensus, but with enough weight and repetition to demand further exploration. The warming of the ocean from below. At first glance, the very idea seems counterintuitive. After all, the surface here is frigid, the wind sharp and unforgiving. Temperatures regularly plunge to depths that would freeze bare skin in seconds. Snowfall drapes the landscape like a funeral shroud, and the ice itself glows with an otherworldly coldness. To suggest that warmth, of any kind, could be part of the equation feels absurd. But deep beneath the surface, far below the frozen expanse, the story shifts. The ocean beneath the ice doesn't mirror the sky above. It harbors currents that flow with ancient momentum, and temperatures that, while still cold by human standards, are warm enough to sculpt the foundation of ice over time. For years now, satellites and underwater sensors have whispered hints of this subtle force at work. Not dramatic, not blazing hot, but steady, persistent. Imagine a candle held near the base of a towering sculpture of wax. The flame does not need to roar. It does not need to burn the surface. All it must do is flicker close enough, for long enough. In the same way, the water lapping at the underside of the ice shelf has been warmer than expected. Just a few degrees. Enough to be dismissed in casual conversation. But not enough to ignore if you understand the sensitivity of ice, especially ancient, compacted ice that has rested undisturbed for thousands of years. These warmer waters don't arrive with fanfare. They slip in silently, carried by deep ocean currents that snake their way toward the poles. Some are remnants of tropical waters that have traveled halfway across the planet, driven by global circulation patterns that are as old as the continents themselves. These currents don't seek destruction. They are merely following paths carved by the rotation of the earth, by wind, by salt, by heat. But when they reach the base of a floating ice shelf, a wall of frozen history held above water by its own buoyancy, the effect can be transformative. Beneath the surface, the interaction begins in the dark, where no human eyes can see. The warm water brushes the underside of the ice. Not enough to melt it instantly, but enough to start thinning it. The process is agonizingly slow, millimeters at first, then centimeters. But as years pass, the change accelerates. Cavities begin to form. Small at first, then larger. Like termites in wood, these hidden pockets begin to weaken the structure from the inside out. They do not announce themselves with cracking or crashing. They simply exist, growing in size, carving out hollows in a world that was once solid. It's this quiet erosion that makes the phenomenon so dangerous. From the outside, everything may appear the same, white, pristine, undisturbed. The surface still sparkles under the pale sun. The ice still towers like a monument. But beneath it, the supports are slowly vanishing. Imagine walking across a frozen lake in winter, unaware that the ice beneath your feet has been hollowed out by warm currents from below. Each step might feel secure, until it's not. This kind of basal melting from the bottom, is particularly insidious. Unlike surface melting, which leaves visible pools and rivers, basal melting occurs in silence. There is no warning, no visual cues. The ice can remain outwardly strong until the moment it isn't. And when failure comes, it can be catastrophic. Because the structure isn't simply breaking from above, it is collapsing from within. And here lies the terrifying potential of what we're seeing now. As the giant wall of ice begins to split and fracture, the scars on its surface may be reflecting damage done far below, damage wrought by water that was never meant to reach it. And while surface temperatures have long been the focus of public discussion, it's this hidden warmth that may be doing the most damage. Because it is patient. Because it is persistent. Because it is unseen. The implications are vast. Scientists studying the region have found increasing evidence of under-ice channels, hidden rivers of water that run between the ice shelf and the sea. These channels act like highways, guiding warm water into contact with vulnerable sections of the ice. The warmth doesn't spread evenly. It moves with the currents, pooling in weak spots, thinning critical areas, and destabilizing the base. Over time, as the support diminishes, the structure becomes vulnerable to its own weight. Cracks appear, pieces start to separate, and eventually the shelf begins to break apart. None of this is immediate. None of it is explosive, at least not at first. It is a slow decay, a quiet dismantling. But when it reaches a tipping point, the transformation can happen with startling speed. A massive slab can detach, as if severed in a single motion. And the result is not just the loss of ice, but the reshaping of an entire coastline. What was once a frozen frontier becomes open water, changing the dynamic of sea levels, ocean currents, and weather patterns across the globe. For now, we still watch. We still measure. We still gather data and interpret patterns. But if the warming of the ocean from below is indeed the driving force behind this unraveling, then we are witnessing not just an event, but the continuation of a process. A process that has been unfolding beneath our feet, hidden from view, operating in silence. And like all hidden forces of nature, its power lies not in how loudly it arrives, but in how deeply it moves before it is ever seen. But how, exactly, does this warmth manage to find its way beneath a fortress of ice that has stood untouched for millennia? That is the unsettling heart of the matter. These are not random intrusions. The warm waters are guided, channeled, by pathways carved not recently, but eons ago. The seafloor itself plays a vital role, acting like a subterranean roadmap for heat. What looks to us like a flat, empty abyss is actually a rugged landscape of ridges, valleys, and troughs, shaped by ancient geological processes long before the first ice ever formed above. Over thousands of years, the ice shelf settled into these underwater contours, forming a tight bond with the terrain below. But time is not static. Tectonic shifts, volcanic remnants, and even the weight of the ice itself have subtly reshaped the ocean floor. Channels that once deflected currents now funnel them directly toward the underbelly of the ice. Some of these channels are narrow and twisting, mere veins. Others are wide enough to be considered underwater highways, several kilometers across, carrying vast volumes of seawater right beneath the glacier's feet. And it's not just the geography that matters, it's also the salt. Salinity determines how water behaves under pressure and cold. Salt water doesn't freeze at the same temperature as fresh water. It remains liquid longer, denser, heavier. This means that even when surface temperatures are far below freezing, saline water can continue its slow journey beneath the ice, nudging against the base, exploiting every slope, every incline, every small fissure in the terrain below. In recent years, scientists have deployed sophisticated robotic submersibles to map these hidden areas in greater detail. The data they return paints a haunting picture, a labyrinth of shadowy corridors where warm water pulses steadily toward its frozen target. Some routes branch off into dead ends. Others go deeper. The temperature differences they've recorded aren't dramatic, often just 1 or 2 degrees above freezing, but over a long enough period, it's like leaving a slow leak under the foundation of your home. At first, nothing changes. But over time, things begin to shift. Now imagine this. You're standing atop a cathedral-sized slab of ancient ice. Everything appears calm. The wind is bitter. The air is sharp. You see nothing out of the ordinary. But miles beneath your boots, there's movement. A low hum of energy. Not audible, not visible, but real. Water, slightly warmer than it should be, is gently carving away at the ice base, undermining it from the bottom. The process isn't violent. It's meticulous, deliberate. Like an artist with a chisel, working not to destroy, but to reshape. This reshaping isn't uniform. And that's critical. Because once the bottom of an ice shelf begins to melt unevenly, pressure redistributes across the entire structure. The shelf begins to bend, not visibly, not like a bridge sagging under weight, but microscopically. These micro changes accumulate over time, causing stress fractures to form in places that once bore no strain. It's as if the foundation of a skyscraper began to settle unevenly. Cracks would appear, doors would jam, windows would no longer fit. The same principle applies here, except on a scale so vast it defies comprehension. To the untrained eye, these initial changes are invisible. Even aerial flyovers with high-resolution cameras may detect nothing out of place. But radar scans and subglacial sonar tell another story. Voids are forming. Cavities. Pockets of space where solid ice once stood. Some of these voids are just a few meters across. Others can be the size of football fields. Empty space beneath a sheet of ice 2 miles thick. A silent warning that the structure is losing its integrity, long before the surface ever shows it. It's here that time becomes the most dangerous variable of all. Because the longer the warm water is allowed to circulate unimpeded, the more damage it can inflict. The ocean doesn't pause. It doesn't sleep. The tides rise and fall. Currents strengthen and weaken. And every single hour, more heat is transferred into the very bones of the glacier. Think of it like a wick on a candle, not the kind you light and watch flicker in seconds, but the kind that burns slowly, steadily, barely noticeable, until one day, the candle is gone. And just as crucial as the presence of warm water is the absence of reinforcement. Once a glacier begins to float more than it rests, once it becomes detached from the grounding lines that once tethered it to the seabed, it loses stability. Those grounding points act like anchor bolts in a storm. They hold the mass steady against ocean forces, against wind, against gravity. Without them, the glacier drifts. Not quickly. Not like a ship. But subtly. It sags. It stretches. And with every shift, its internal structure weakens further. This floating phenomenon, known as hydrofracturing, can trigger secondary effects. Meltwater, for instance, can seep into crevasses during the warmer months. When that water refreezes, it expands. Like a wedge in a rock, it forces the crack wider. Over time, this freeze-thaw cycle escalates until the glacier begins to cleave from the inside. Again, all of this is happening as the ocean continues its relentless whispering from below. And what happens when the support finally gives way? When the ice, thinned and hollowed and stressed from within, can no longer support its own weight? That's when you see the dramatic, headline-grabbing moment, the fracture, the break, the sudden release. But by then, it's too late. The damage has already been done, quietly, methodically, over decades. The break is simply the conclusion of a much longer story. This isn't the future. It's already happening. Across vast stretches of the polar regions, researchers are finding that the rate of basal melting has increased exponentially in recent years. The once solid, grounded shelves are beginning to lose contact with the seabed. The warm currents are finding new paths. The voids are becoming more frequent. And the warning signs are growing louder, not through explosive events but through silence. Through thinning ice. Through stress fractures. Through changes that can only be seen through instruments pointed at the invisible. All of this points to a chilling conclusion. The slow warmth from below is not an anomaly, it's a force of change. A force that may have been active for much longer than we've understood. A force that does not roar but whispers. And when it finally speaks loud enough for the world to hear, it may already be too late to stop what's coming. Beneath the pristine, frozen surface of our planet's polar regions, where silence reigns and snow blankets the earth in stillness, a startling truth simmers, one that feels almost like a contradiction. It's the presence of fire, heat, and molten rock lurking beneath all that ice. And in the case of the massive wall of ice currently cracking and drifting apart, one theory gaining quiet momentum among glaciologists and geophysicists is as bold as it is unsettling. A volcanic system may be stirring beneath the ice, exerting invisible pressure from below. This isn't science fiction. It's a geologically supported phenomenon. Antarctica, for instance, sits atop one of the most volcanically active regions on Earth. Over 100 known volcanoes lie hidden beneath its thick sheet of ice, their jagged peaks buried under kilometers of glacial mass. Some are dormant. Others are considered active. And a few, according to recent seismic readings and thermal anomalies, may be quietly rumbling back to life. Subglacial volcanoes are not like their more dramatic cousins that spit lava into the sky and shower nearby towns with ash. Their eruptions are muffled, sometimes never even breaching the surface. When they do stir, they often release slow pulses of geothermal heat. No firestorm. No mushroom cloud. Just a steady exhalation of energy beneath a glacial tomb. Now imagine what that means for a massive ice shelf resting above such a system. At first, the heat goes unnoticed. After all, the ice sheet is miles thick in some areas. But over time, the base begins to respond. The most immediate effect is melting, not at the surface, but at the interface between rock and ice. The glacier, once frozen solid to the bedrock below, begins to detach. Water pools into subglacial lakes, lubricating the base. Ice that was once locked in place becomes mobile. Gravity does the rest. And it's not just heat in the traditional sense. Subglacial volcanic activity can also lead to gas emissions, carbon dioxide, methane, and even sulfur. These gases can rise through microscopic cracks and crevices within the ice. In confined areas, they can build pressure over time. That pressure doesn't need to be explosive to cause instability. It only needs to shift the internal balance. Like inserting a balloon between two bricks, eventually, one of them gives. What makes this process so insidious is how undetectable it can be until it's too late. Satellites can't see through thick ice. Surface temperatures may show no sign of change. And seismic activity, unless it's extreme, is often masked by the natural creaks and groans of the shifting ice sheet. In many cases, it's only after the damage has begun to manifest, after massive calving events or mysterious structural collapses, that researchers piece together the signals retroactively. Thermal imaging from deep ice boreholes and ice-penetrating radar has started to paint a more complex picture of what's happening beneath these icy giants. In some areas, the base of the glacier is far warmer than it should be, sometimes 30 or even 40 degrees warmer than the air just a few hundred meters above. In isolated pockets, sensors have picked up tremors, faint, rhythmic pulses that don't match typical tectonic patterns but instead suggest magma movement or gas buildup. Consider this. In 2017, a group of researchers discovered over 90 previously unknown subglacial volcanoes in West Antarctica alone. These weren't just bumps in the rock. Many were aligned in linear patterns, suggesting they belonged to larger volcanic chains or rift zones, systems that could, in theory, behave collectively. A single eruption might not be enough to destabilize an entire ice wall. But what if there were several, working in tandem? Even without full eruptions, the cumulative heat and pressure from a volcanic field could slowly undermine a glacier from the base up. And what makes the situation even more precarious is the fact that ice, as rigid as it appears, is sensitive. Delicate. It's a structure held together by compression and cold. When the base begins to change, when it's no longer anchored to cold rock but instead hovers above warm water or unstable ground, the internal tension starts to redistribute. Microfractures begin to form. Pressure mounts not just vertically, but laterally, spreading like veins of instability throughout the entire mass. Subglacial volcanic activity can also cause isostatic rebound. When ice melts due to geothermal heat, the weight pressing down on the crust is reduced. The ground beneath begins to rise. This vertical movement, though often measured in centimeters or millimeters per year, can dramatically alter stress points within the glacier. It's like shifting the foundation of a building 1 inch to the left. The walls don't crumble immediately, but the integrity of the entire structure begins to degrade. These subtle, accumulating shifts, melting at the base, rising ground, increased basal lubrication, silent gas expansion, eventually reach a tipping point. Suddenly, the glacier that appeared stable becomes a ticking clock. The ice starts to deform from within. Not violently, but persistently. And eventually, the forces keeping it together lose their grip. You don't need an explosive eruption to witness collapse. Just a steady release of heat in the wrong place at the wrong time. The tragedy here is not in the suddenness, but in the slowness. A volcano doesn't need to roar to change the world. Under the right circumstances, it only needs to whisper beneath the ice. And so, as scientists analyze satellite data and ice core samples, more and more are beginning to suspect that what we're witnessing may not be purely atmospheric in origin. There may be something alive beneath that wall of ice, something ancient, quiet, and patient. A heat that has waited for centuries, pressing upward with unrelenting persistence. It's not a storm, not a man-made error. It's Earth itself, reaching up from the deep. The mystery continues to unfold. But this theory, volcanic activity beneath the ice, may hold the key to understanding why such a massive, seemingly immovable ice formation has begun to fall apart. Slowly, methodically, almost as if summoned by a force hidden in the dark. To truly grasp the gravity of what might be unfolding beneath the ice, it helps to understand just how unique and complex subglacial volcanic systems are. Unlike open-air volcanoes, which offer visual cues, smoke plumes, lava flows, ash clouds, subglacial volcanoes are masked by layers of compacted snow, pressurized ice, and frozen silence. Their behavior is shrouded not only in mystery but in insulation. It's this concealment that makes them such formidable agents of change. Not because they act quickly or loudly, but because they move in the shadows, unseen and unchecked. Picture this: beneath kilometers of glacial cover lies a volcanic fissure, a long, narrow fracture in the Earth's crust, slowly emitting heat. It doesn't erupt in the cinematic sense. There's no catastrophic explosion or lava geyser. Instead, the fissure bleeds warmth. Gradually, this heat works its way up into the base of the ice above, not as a firestorm, but as a relentless thermal seepage. It's the kind of change that escapes headlines. But over decades, that warmth rewrites the physics of an entire ice sheet. And it's not just heat, it's the dynamic interplay of pressure, mineral exchange, and thermal conductivity that starts to reshape the interface between the Earth and its frozen skin. The rock beneath the ice doesn't remain static. It expands subtly as it heats. It becomes more brittle in some areas, more ductile in others. This uneven response introduces a patchwork of mechanical stress into the overlying ice, a complex quilt of invisible strain. Over time, these imbalances can cause deep internal shifts, even before any visible signs appear on the surface. Moreover, subglacial volcanic zones often sit within rift systems, places where tectonic plates are slowly drifting apart. In these regions, the Earth's crust is naturally thinner, more prone to cracking, and more permeable to ascending magma and geothermal fluids. These rift zones act like geothermal lungs, exhaling steady streams of energy that get trapped under the ice. The heat isn't centralized, it spreads out, diffusing laterally, affecting wide swaths of the glacier's base. In effect, an entire region can become destabilized not by one violent event, but by a quiet, collective exhalation of heat. This basal heating doesn't melt the ice uniformly. It creates channels, runnels, voids. Some sections may develop vast subglacial lakes, while others become riddled with porous ice that lacks the structural cohesion it once had. These inconsistencies beneath the surface create tension zones. Areas that were once frozen solid are now undercut, unsupported. Stress begins to localize in ways no human eye can see. The glacier, in essence, becomes internally hollowed out. What's particularly unnerving is that as this process continues, the feedback loop strengthens. Meltwater generated at the base doesn't always remain static. It can flow, sometimes in great volumes, lubricating the interface between the glacier and the rock. This reduces friction dramatically. A glacier that was once frozen into place now glides on a slick film of pressurized water. Movement begins. Not always fast. Not always dramatic. But enough to change the stress distribution throughout the entire structure. As the glacier slides or sags in response to this undermining, crevasses open up at the surface. These aren't just superficial cracks. They can extend deep into the ice, acting as conduits for warmer air, seasonal meltwater, or even rain from above. And that meltwater, when it finds its way back to the base, only accelerates the heating process further. In this way, a simple, localized heat source from below can end up amplifying itself through surface-level consequences. The system becomes self-reinforcing. And still, there's more. The chemical interaction between the geothermal environment and the glacial ice can also lead to unforeseen consequences. Trace elements leaching upward from volcanic vents, iron, sulfur, and even chloride, can alter the structural integrity of the ice crystals themselves. While this seems like a minor point, over vast scales, these tiny chemical alterations can affect the way ice flows, how it fractures, and how it refreezes. Even more obscure are the implications of seismic resonance. Volcanic systems, even dormant ones, emit low-frequency vibrations known as harmonic tremors. These are not earthquakes in the traditional sense. They're more like the earth humming quietly to itself. And while imperceptible to us, this constant vibration can cause internal oscillations in the glacier above. Think of it like gently shaking a sheet of glass. No immediate damage. But over time, those vibrations can initiate fractures along weak planes, micro-fissures that compromise the internal lattice of the ice. These vibrations may also interact with meltwater dynamics. Subglacial lakes and water channels can begin to resonate with harmonic tremors, like water in a glass responding to sound waves. This can lead to sudden discharges, rapid redistribution of subglacial water, and localized collapses that act as precursors to larger, more catastrophic structural failures. And then, of course, there's the temporal element. These processes don't just unfold over days or weeks. They can span centuries. The heat from a deeply buried magma plume might take decades to make its presence felt, and yet by the time signs emerge, the destabilization may already be irreversible. What we interpret as sudden ice loss might actually be the delayed consequence of a volcanic awakening that began generations ago. This possibility, that an ancient, slow-burning geological process could be culminating now, in our lifetimes, is what makes this theory so compelling, and so chilling. It reframes the narrative. This isn't just a story of ice and cold. It's a story of time, of hidden energy, and of the deep, inexorable forces that shape our world from beneath. And so we watch, and we measure, and we model. But even with all our tools and satellites and simulations, there remains something profoundly mysterious about this idea, that the ground beneath the ice might not be passive, but alive. That beneath the stillness, there is movement. Beneath the cold, there is heat. And beneath the silence, there is sound. As we drift deeper into the complex web of possible explanations behind the unraveling of this massive ice formation, our perspective pivots once again, this time downward, beyond the ocean floor, beyond the layers of ancient sediment, into the Earth's own interior. Here, nestled beneath the frozen vastness of Antarctica, lies a world of unseen movement. A realm not governed by tides or wind, but by the slow, relentless churn of molten rock and thermal energy. And it's in this hidden world, some believe, that a long-dormant force may have stirred. The theory, while speculative, is compelling, that deep beneath the ice lies a network of geothermal anomalies, pockets of concentrated heat energy capable of sending sudden pulses upward, like breaths from the planet's core. These are not your typical volcanoes or obvious geothermal vents. No, these are subtler, more elusive. Not eruptions, but pulses, brief but potent waves of energy that rise through cracks and weaknesses in the lithosphere, seeping upward and warming the massive ice sheets from below. To understand this potential phenomenon, we must first consider the geological uniqueness of Antarctica itself. Beneath the thick glacial blanket, the continent is anything but flat. It's a patchwork of mountain ranges, buried valleys, rift systems, and fault lines, many of which remain largely unstudied due to the sheer difficulty of accessing them. And within this chaotic mosaic, there are signs, faint but persistent, of geothermal hotspots. Not unlike those found in Iceland or Yellowstone, these thermal anomalies are thought to be remnants of a dynamic mantle plume system, where heat from deep within the earth breaches the crust at unpredictable intervals. Now imagine, just for a moment, that one of these ancient conduits has reawakened. It wouldn't be explosive. It wouldn't send lava spewing into the air. But it would release heat, immense heat, quietly, efficiently, and directly into the base of the overlying ice. The result? A slow but concentrated melting from within, carving out hollow chambers in the ice sheet's underbelly. Over time, these subterranean voids could grow, forming lakes and rivers of meltwater that no surface observer could detect. What makes this idea particularly unsettling is how undetectable it could be in its early stages. Standard satellite imagery is blind to what happens beneath kilometers of ice. Most sensors are calibrated to detect surface temperature anomalies, not subglacial thermal surges. That means a geothermal pulse could have already occurred, or be happening right now, without any immediate signs on the surface. The ice might appear stable from above while its base thins, destabilizes, and begins to fracture from hidden stress points. And while the idea of heat seeping up from below may seem dramatic, it is not without precedent. Researchers have already confirmed the existence of a vast subglacial lake system in East Antarctica, fed by geothermal heat. There are areas where ice flows more rapidly than expected, where basal lubrication appears too high to be explained by surface melt alone. These regions are suspected to sit atop thermal anomalies, warm spots that keep the ice sheet ever so slightly elevated from its base, gliding it forward with a slick layer of meltwater acting as an unseen conveyor. But what if the behavior of these hotspots isn't constant? What if the Earth itself is breathing in cycles? Long, slow, geological breaths that span centuries or even millennia. A thermal pulse every 1,000 years, or 10,000. A heartbeat so slow, it escapes notice during a human lifetime. If such a pulse were to strike now, after remaining dormant for ages, it could destabilize the very foundation of an ice shelf, not over decades, but in a matter of months or even weeks. The sudden introduction of warmth would not just melt the ice, it would reshape it. As the base softens and liquefies, the overlying layers could buckle and shift, forming crevasses and pressure ridges. The integrity of the structure would be compromised not by weather or climate, but by a slow upheaval from beneath, a betrayal by the very bedrock it rests upon. Geophysicists speculate that there may be over 100 of these thermal anomalies beneath Antarctica, many of which remain unexplored. Some are thought to be ancient magma chambers, cool but still active at their fringes. Others could be tectonic stress points, where friction generates localized heating. It is entirely possible, if not yet provable, that one such anomaly lies directly beneath the ice wall now beginning to collapse. And in the grand scheme of Earth's history, this would not be unusual. The planet is a restless sphere, prone to shifting, adjusting, and releasing energy when internal thresholds are breached. From time to time, these bursts of geologic energy find their way to the surface, expressing themselves through fault ruptures, gas emissions, or, in this case, concentrated warmth rising into one of the most delicate systems on Earth. While mainstream science might consider such geothermal pulses rare or even unlikely, the sheer strangeness of recent events demands that we look beyond the comfortable explanations. The timing, the scale, the sheer violence of the ice collapse, these things beg for a broader lens. And in that broader view, the Earth's own secret breath might just play a role. If this theory holds even a sliver of truth, the implications are staggering. It means that not all of our efforts to model, predict, or mitigate ice loss can account for what stirs beneath our feet. That while we look to the skies and measure the heat of the sun, we may be overlooking the quieter, older fire, one that smolders within the Earth itself. So we are left to wonder, could this massive wall of ice be not merely melting, but being unseated by the invisible hand of a geothermal breath? A pulse from the planet's ancient heart? Perhaps the ice isn't just reacting to surface changes, but responding to a call from below. What happens when something as colossal, ancient, and seemingly immovable as a massive Antarctic ice wall begins to break apart? What happens when that frozen monolith, one that stood for thousands upon thousands of years, cracks, fractures, and begins to slide into the sea? It doesn't just vanish quietly into the night. It doesn't dissolve harmlessly, like sugar into water. No, an event of that magnitude doesn't simply happen. It echoes. It reaches out across oceans and atmospheres. And its message? It's urgent and it's personal. Because when the balance of the Antarctic ice is disrupted, it's not just a regional problem. It's a planetary shift. And the first messenger of that shift is the sea. Coastal cities, those shining beacons of modern civilization perched at the water's edge, suddenly find themselves vulnerable in ways that spreadsheets and zoning maps can't quite convey. We're talking about places like New York, Miami, Mumbai, Lagos, Jakarta, and countless others where skyscrapers stretch toward the clouds, but whose foundations lie barely a meter or two above rising tides. When a single wall of ice the size of a small country begins to crumble, it isn't dramatic because it's far away. It's dramatic because it brings the ocean closer to every doorstep. The sea doesn't rise in a dramatic tidal wave, not right away. Instead, it creeps. It infiltrates. It saturates groundwater, corrodes pipelines, buckles roads, seeps into subway systems. It makes once developable land permanently soggy. And it doesn't care how advanced your civilization is. It doesn't care about borders or infrastructure budgets. It simply follows gravity, spreading out evenly across the world's oceans, lifting them inch by inch, year by year. But perhaps more subtle, and far more insidious, than sea level rise is the destabilization of global systems that depend on climate regularity. You see, the polar regions are the planet's thermostats. When they change, everything downstream shifts. And the polar south, in particular, plays a massive role in regulating ocean currents. The Antarctic Circumpolar Current, the largest ocean current on Earth, is driven in part by temperature gradients created by the stability of the ice. Disrupt that, and you're not just moving water, you're rearranging the entire conveyor belt of heat and nutrients that flows through the world's oceans. This could throw off weather patterns in ways that don't feel immediately connected but are. Imagine heat waves hitting Europe with more frequency and ferocity. Picture monsoons in Asia arriving late, short, or not at all, disrupting the agricultural cycles of billions. Consider droughts deepening in regions already parched, while floods pummel others that once knew only light rain. These are not isolated natural events. They are chain reactions, triggered not by storms or emissions alone, but by the very architecture of our planet shifting beneath us. And then there's the human dimension, the psychological rupture that comes with realizing that our most basic assumptions about the natural world no longer hold. We assume the ice is eternal. We assume the poles are distant. We assume nature changes slowly, predictably. But what happens to the human spirit when those assumptions are shattered? When the ice cracks and the tides surge and we realize we were never as in control as we thought? Some communities will adapt, as they always have. But others, particularly those already on the margins, economically, geographically, politically, may be forced to make impossible choices. Do they relocate? Retreat? Reinvent their livelihoods? Entire populations could be displaced not by war or famine or political upheaval, but by the slow, unstoppable march of water. This isn't the stuff of speculative fiction anymore. It's the quiet, creeping edge of a reality we're beginning to glimpse. Even the economic landscape could quake beneath the pressure. Insurance companies may start pulling coverage from coastal properties, triggering real estate collapses in formerly booming markets. Shipping routes could shift as currents and ice paths change. Food prices might fluctuate more wildly, as crop yields bend to increasingly erratic weather. And in the background of it all, governments will be forced to reckon with an unfolding crisis they cannot legislate away. But perhaps the most haunting aspect of this scenario is its asymmetry. Some places will be hit hard and fast, others more slowly. And this unevenness could stir unrest, political and cultural ripples that emerge when some nations feel the storm first, and others watch from the sidelines until their turn comes. Still, in the shadow of such a monumental shift, there is also a rare moment of unity to be found. Because what breaks the ice doesn't just fracture nature, it fractures complacency. It pulls us out of the ordinary, out of our routine patterns of thought and consumption, and forces a reckoning. A new humility before the forces that govern this world. A new urgency to think not just about today, but about the decades ahead. About the kind of planet we're shaping, not just for ourselves, but for every generation that follows. This wall of ice, breaking apart at the bottom of the world, is more than a geological event. It is a warning bell. A whisper carried on the winds and waves that says, pay attention. Because what comes next could reshape the world not in an instant, but in 1,000 quiet, cascading ways. At the beginning, it may have seemed like just another headline lost in the ever-spinning carousel of global events. A wall of ice breaking apart in a faraway polar land, Antarctica, a continent so distant and removed that, for many, it exists only in textbooks and satellite imagery. But as we've journeyed deeper into the haunting story behind this monumental fracture, a very different picture has emerged. One that is intimate, intricate, and undeniably relevant. We began by simply observing a massive, seemingly immovable wall of ice beginning to crack and crumble. Not just a piece here or a sliver there, but whole sections destabilizing, massive shelves groaning under invisible forces and slipping into the frigid Southern Ocean. It was easy, at first, to think of it in geological terms, to picture chunks of ice falling and floating, eventually melting and merging into the sea. But we didn't stop at the surface. Instead, we dug deeper into what might be causing this vast and ominous shift, unpacking a series of complex, layered, and often unnerving possibilities. Our first exploration took us into the realm of warming ocean currents, an invisible force wrapping around the southern pole like a tightening noose. This wasn't just about the air getting warmer, but about deep, subsurface waters gaining degrees over time. These warmer currents, sneaking beneath the ice shelves, silently erode the very foundation of Antarctica's icy armor. No alarm bells. No dramatic signs above the surface. Just a slow-motion assault from below, carving tunnels and hollows until the ice collapses under its own weight. From there, we transition to a second potential catalyst, tectonic instability. While earthquakes and seismic shifts are often thought of in terms of destruction on land, we entertain the lesser-known reality that such underground movements also reach beneath Antarctica's crust. We talked about stress accumulation over millennia, how ice can act like a lid trapping pressure beneath it, and how a sudden tectonic release might be capable of jolting an entire shelf free. We considered the buried mountains, the ancient fault lines, the slowly grinding plates that could someday slip, shifting not just land, but history. Then, we drifted into the next theory, volcanic heat simmering beneath the ice. Not speculation, but something grounded in discoveries of subglacial volcanoes, dormant giants capable of waking up and altering the very climate around them. The slow but consistent heat from these hidden furnaces could weaken ice from below, making it fragile and ripe for collapse. And what could result from that? More than just melting, potential destabilization of whole regions, changes in local and global weather patterns, and the unleashing of ancient sediments and gases long trapped beneath. And then, we ventured into the more speculative, a theory leaning into the edge of believability, yet not without its own peculiar logic. We entertained the idea that unknown forces, perhaps even geoengineering experiments gone awry, or phenomena we don't yet understand, might be at play. Semi-believable but fascinating nonetheless, this theory was more about the human tendency to reach for answers in the face of mystery. To piece together stories from threads of science, suspicion, and imagination. Because when something so vast and stable begins to falter, it's only natural to search every possible crevice for understanding. But theories aside, the real weight of this unraveling story came when we finally asked, what does this mean for us? We peeled back the distant layers and realized that this isn't a remote problem confined to polar explorers and climate scientists. No, this is a deeply human concern. Because when Antarctica's great ice walls falter, the oceans respond. And when the oceans rise, so do our fears, our challenges, our stakes. Coastal cities could become cautionary tales of overconfidence, entire metropolises built in defiance of the sea now learning to bow to its return. Economies could sway more violently than we imagine, as insurance markets shift, property values nosedive, and food supplies feel the pressure of disrupted global patterns. Even international relations might strain under the pressure of mass migrations, shifting resources, and the deepening divide between those who can adapt quickly and those left behind. Weather patterns could become unfamiliar. Regions accustomed to predictable cycles might see droughts, floods, or snow where none once fell. The planet's delicate balance, held in place by temperature gradients and oceanic conveyor belts, may tilt, not in a dramatic cinematic collapse, but in a relentless, uneven shuffle that leaves no corner untouched. And then there's the psychological toll, the shift in collective consciousness that occurs when something as permanent as polar ice proves temporary. The recognition that we live not atop a stable world, but a breathing, changing, living planet, one whose systems stretch far beyond human timelines or control. This realization can be both terrifying and galvanizing. Terrifying in its scale, galvanizing in its call to action. Because as massive and overwhelming as this may seem, it is not the end of the story. It is the beginning of awareness, of urgency, of a deeper respect for the forces shaping our world. And perhaps most importantly, it is a moment that invites us to think beyond ourselves, to consider the inheritance we leave behind, the legacy carved not just in stone or steel, but in how we treat the Earth itself. In the end, the great Antarctic ice wall breaking apart is more than a visual spectacle or a scientific curiosity. It is a mirror. It reflects not just the warming waters or shifting plates beneath it, but our own fragile sense of permanence. It reveals how small changes in one corner of the world can ripple across continents, touching every life, every shore, every future. So now, the question isn't simply what comes next for the ice. The real question, the one that echoes across oceans and reverberates through time, is, what comes next for us? And in that answer lies the future we're all still writing. If you found this video intriguing, informative, or thought-provoking, make sure to give it a thumbs up. It really helps more people discover stories like this. And if you want to stay up to date with more deep dives into the mysteries shaping our world, hit that subscribe button and turn on the notification bell so you never miss an upload. We've got plenty more fascinating topics on the horizon, and trust me, you won't want to miss what's coming next.